So our first speaker in this morning's session is John Preskill, who's going to tell us about Steve Weinberg's universe. Thanks, John.
Well, hi, everybody. I'm honored to be here. I'm going to talk about Steve Weinberg. With an emphasis on his contributions to cosmology, it's not that I think that's the most important part of his scientific legacy. The truth is, I had the opportunity to give a talk on this subject at a previous symposium in Steve's honor, so I'm dusting that talk off, hoping it'll be of interest to this audience. This may be superfluous, but we'll start with Steve's life story. He was born in New York. He attended the Bronx High School of Science, which counts 7 Nobel laureates among its alumni, including Steve's classmate, Shelley Glashow. He attended Cornell and he met Louise there. They got married after graduation. He spent a year in Copenhagen and got his PhD at Princeton, advised by Sam Treman. He was a postdoc at Columbia and at Berkeley, then joined the Berkeley faculty. And when Louise moved east to start at Harvard Law School, Steve took at first a visiting appointment and later became a professor at MIT. Elizabeth was born in Berkeley, and Steve later recalled that he did a lot of his thinking in the MIT years, sitting on park benches watching Elizabeth play. He moved to Harvard in '73 and then to the University of Texas in 1982, where he spent the rest of his career. And he died at age 88 in 2021. He was scientifically active into his final year. Steve received many honors and distinctions, most notably the Nobel Prize in Physics and the National Medal of Science, both recognizing his contributions to the standard model of particle physics. Steve had some distinctive characteristics as a researcher. He was solitary in the sense that most of his papers are single author, but he always consulted extensively with colleagues. Many of us in the room, I suspect, had the experience of getting a phone call or an email from Steve seeking clarification of some technical point. He was not a visual thinker at all. He believed in the power of equations rather than figures to convey scientific ideas. I remember him telling me how annoyed he was when the Windows operating system launched and he would have to click on an icon instead of writing into the command line. He liked notation to be explicit. Steve would put indices on indices. And if it was different notation than anybody else used, he didn't mind. He thought his notation was better, so he was going to use it even if other people didn't like it. His papers were often very general and methodical, seeking and often succeeding in reaching sweeping conclusions from general principles. But he was quite successful at connecting formal things to real phenomenology. He was meticulous about who he would reference in his papers, and he expected the same courtesy in return. He was quite scholarly about history, and in particular, the history of science. When he would teach a course, he would almost invariably begin with a survey of the history of the subject before he would pivot to the unitary representations of the Poincaré group, which he seemed to think was the right way to start teaching any subject. He was a gifted communicator, and he worked very hard in both what he spoke and what he wrote to be as clear as possible. He was not a model builder because models are usually wrong, and he much preferred to reason from principles that had firm foundations. So it's quite ironic that his best-known scientific contribution, for which he received the Nobel Prize, was a model of leptons. He liked to keep the TV on his desk while he was working. I asked him why. He said, well, it makes it much easier to return to my desk after a break if I can just watch an old movie for a while. It helps ease me into the work again. In an interview, he said, I need the distraction to keep at my desk because the actual work is so, well, it's so chillingly non-human. I need to feel like I am still part of the human race while I'm doing it. Well, I reviewed Steve's 50 top-cited papers. 42 are single author. These are the 16 that, according to Google Scholar a few days ago, have 2,000 or more citations. I put in red the ones that have something to do with cosmology. Even when he collaborated, he preferred to write the paper himself because he didn't like how other people write. His most cited collaborative paper was the one with Goldstone and Salam on the proof of the Goldstone theorem. And in that case, the writing was shared, and there's an argument that's based on perturbation theory, which is obviously Goldstone's, and one that follows from general principles, which is obviously Weinberg's. So even in a case like that, his voice would shine through clearly. And he not only wrote papers, he wrote books, lots of books, 15 books, both textbooks and popular books. The textbooks are comprehensive and authoritative. The popular books, generally speaking, were warmly received. I think part of the reason Steve was so successful at connecting with lay audiences was that he really respected his readers. He realized that even if not scientifically trained, they were intelligent and expected well-reasoned arguments, and he would try to provide those as clearly as possible. I arrived at Harvard as a graduate student in 1975. My generation came along a little bit too late to participate in formulating the standard model of particle physics. That was pretty much in place in the mid-70s. But there were a lot of exciting, fresh ideas floating around. These are some of the ones that I found exciting at the time. In the Harvard particle theory group in the late 70s, most of the students flocked to Howard Georgi because he was so approachable and such a great mentor, or to Sidney Coleman because he could give a lucid, off-the-cuff answer to almost any question. And Steve didn't have those qualities. But as I thought about it, I felt that the scientific thrusts that had the greatest potential to lead to important discoveries were probing the early universe, looking for relics of very short distance physics, and exploring potential new strong interactions responsible for the breaking of electroweak symmetries. I thought that was our best hope for understanding the quark and lepton masses and mixing angles, which I thought at the time was the central phenomenological problem. Steve was working on those things, so I wanted to be a student. And he never gave me any advice. He never told me to do something or to not do something, but he was a frequent source of inspiration. And of those two topics, the latter didn't really pan out, but the former, the connection between particle physics and cosmology, became a thriving subfield. This doesn't have anything to do with cosmology, but I threw it in because Steve would often refer to it in later years as the one time he solved a mathematical problem. And arguably, it was his first paper that had some enduring scientific value. Weinberg's theorem is really a statement about the convergence of multiple integrals. It's important for physics was that it completed the perturbative renormalization program that had been launched by Dyson and sharpened by Salam. That is, it finished the proof that if you include all counterterms systematically, then Feynman diagram perturbation theory would converge order by order. The argument is very thorough, but not at all elegant. It's brute force, and both Steve and Arthur Whiteman told me later that before publication, Steve gave a copy of the paper to Whiteman and asked for comments, and Whiteman returned it with the comment, "There's blood on every page." So Steve Weinberg was a particle theorist. So how did he become an expert on cosmology? He remembered that when he was in high school, he had read popular books. He had learned that the big question of cosmology, the precision measurement of the Hubble constant and the deceleration parameter, was going to be settled by the Palomar telescope. We're still working on that one. And so He didn't take it that seriously. He didn't get really interested in cosmology until he was a postdoc. And he read Bondi's book. And that's when he learned that you could, from the principle that the universe is homogeneous and isotropic, derive the Friedman-Robinson-Walker metric as a solution to the Einstein equations. He thought that was very beautiful, and it boosted his confidence that theorists had something useful to say about cosmology. Before the microwave background was discovered, Steve was partial to the steady state cosmological model. He really liked that because you didn't have to worry about initial conditions or evolutionary effects, it had stronger predictive power. And his first foray into cosmology was a study of whether a degenerate neutrino background could be detected in a cold Big Bang model. But after the microwave background was discovered, Steve recognized that there were going to be scientific opportunities. He wanted to learn cosmology more deeply. So he taught a course, first at Berkeley, then again at MIT, and the notes for that course became a textbook. Actually, there were 3 books on gravitation and cosmology that appeared in the early 1970s. I acquired copies of all of them at that time. I pulled them off my bookshelf to take this picture. The books by Peebles, Weinberg, and Misner, Thorne, and Wheeler. I think you could objectively conclude that of the 3, after 50 years of use, Steve's is the one that's has the most wear. These books are very different in scope and in style. Steve's book characteristically has almost no figures except for a few charts and graphs. Misner, Thorne, and Wheeler has many very well executed, hundreds of well executed illustrations. There's a lot of cosmology in Steve's book, including a 140-page chapter called The Standard Model, which I think was Steve's locution for the hot Big Bang. Misner, Thorne, and Wheeler use that term as well. Now, this book is aggressively anti-geometrical. Steve wrote, "I believe that the geometrical approach has driven a wedge between general relativity and the theory of elementary particles. The passage of time has taught us not to expect the strong, weak, and electromagnetic interactions can be understood in geometrical terms, and too great an emphasis on geometry can only obscure the deep connections between gravitation and the rest of physics." Now, that anti-geometrical viewpoint has not stood the test of time. So where did it come from? In fact, in the mid-1960s, Steve had written a series of deep papers from which he drew the conclusion that a massless spin-2 field, in order to couple consistently to matter, had to couple universally to the energy momentum tensor. That is, the principle of equivalence would need to be satisfied. And he was not the first to discuss this idea, but his argument was especially general and compelling. So he felt strongly that the principle of equivalence is the right place to start in the theory of gravitation, and if that leads to the Riemann tensor, so be it. But he objected to starting with the idea that gravitation should be described in terms of Riemannian geometry. Peebles, in his Nobel lecture, said, "The 2 books, Peebles and Weinberg, signal the change of cosmology from its near dormant state in the early 60s to the start of a productive branch of research in physical science by the late 60s. And Steve himself, a few years later, wrote, "I remember that during the time that I was a student and then began my own research on other problems in the 1950s, the study of the early universe was widely regarded as not the sort of thing to which a respectable scientist would devote his time. Nor was this judgment unreasonable. Now, in just the past decade, all this has changed. A theory of the early universe has become so widely accepted that astronomers often call it the Standard Model." Steve worked really hard on this book for several years, and later he concluded that that had been a mistake. He said, "I should have dropped everything I was doing and worked on proving that the spontaneously broken gauge theories were renormalizable. I'd rather make discoveries than write books." Well, nevertheless, he wrote a lot of books, and many of us are glad that he did. And he managed somehow to make a few discoveries along the way as well. Steve's first popular book, The First 3 Minutes, appeared in 1977. It was based on a public lecture that he gave for the first time at Harvard in 1973. And it was well received by both professional physicists and scientifically literate non-physics readers. On the jacket of the book, Isaac Asimov said, "What I had thought to be the guesswork and semi-mysticism of scientists turns out to be nothing of the sort. And you have no idea how wonderful that makes me feel." And Bob Dickey, who, by the way, deserves great accolades for his own contributions to our understanding of the early universe, said, "It is an exciting book, and I recommend it for both laymen and scientists. It is comprehensive to the former, significant to the latter, and interesting to both." The title, The First 3 Minutes, was a stroke of genius. It contributed to the success of the book, I think, but it did invite jokes. I remember Leon Letterman coming to Harvard to give a colloquium shortly after the book appeared, and he began his talk with a story. He said he had gone into a bookstore and asked if they stock The First 3 Minutes, and the bookseller said, "Yes, we do, and we're selling a lot of them." And Letterman said, "Well, isn't it unusual for a book about science to sell so well?" And the bookseller said, "Science? I thought it was about sex." Now, as evidence that the book had an influence on scientists, I can quote Allen, who, speaking of the first time he gave a seminar about cosmic inflation, said, "There was also the fear that I would reveal my status as a greenhorn cosmologist. To shore up my general background in cosmology, I had crammed from Steven Weinberg's excellent popular book, The First 3 Minutes." There had been an important change in the study of the early universe between 1972, when gravitation and cosmology appeared, and 1977, when The First 3 Minutes appeared. And that was the discovery of asymptotic freedom. That made it possible to consider the thermal history of the universe at times much earlier than the first 100th of a second. In 1972, one didn't really know what to say about how the hadronic soup would behave at temperatures of 100 MeV and above. By 1977, we could envision a weakly coupled quark-gluon plasma and follow its history back almost to the Planck time. And that made it possible for Allen, in a brilliant seminar that I heard a little bit later at Harvard, to use the title 10 to the minus 35 seconds after the Big Bang. Neutrino cosmology arose in the 1970s. Kausick and McClellan had observed that neutrinos would be about as abundant as photons, and so if they were too heavy, their mass density would overclose the universe. And from that, they inferred an upper bound on the mass of the heaviest neutrino of about 40 electron volts. And Steigman, Schramm, and Gunn had noted that as we increase the number of neutrino species, that increases the expansion rate of the universe at the time of nucleosynthesis, which means there's less time for neutrons to decay before they get bound into nuclei, and that raises the helium-4 abundance. And they concluded from that that there couldn't be more than 3 generations of quarks and leptons. Now, Lee and Weinberg made an important step in 1977. Because they were able to consider the history of the universe at times when the temperature was in the GeV and above, argued that neutrinos would be in thermal equilibrium because of the weak interactions at sufficiently high temperature, but as the universe cooled, the annihilation would eventually cut off because the expansion rate would become larger than the annihilation rate. And if that decoupling occurred when the temperature was sufficiently small compared to the neutrino mass, the abundance of neutrinos would be very highly suppressed by a Boltzmann factor. But if the temperature at that decoupling was not so small compared to the mass, then the neutrino abundance would be too high, and the mass density due to neutrinos would be unacceptably large. And on that basis, they argued that it would be okay to have a neutrino mass, which was 2 GeV or greater. That same argument was then used a few years later in the context of weakly interacting massive particles predicted by some models of physics beyond the standard model to argue that the WIMP abundance could be about right to explain the cold dark matter in the universe. So people enthusiastically look for WIMPs and unfortunately still haven't found them. Ben Lee was a great physicist who was just coming up to speed in cosmology in 1977 under Steve's tutelage. And tragically, just a month after this paper was submitted, he was killed in an automobile accident. He was 42. Now, the discovery of asymptotic freedom and speculations about grand unification made it possible to revisit an enduring mystery in cosmology. Why is there an excess of matter over antimatter? And why is that excess so small compared to the entropy of the universe? We could envision that the universe started out at high temperature in a baryon number symmetric state. And because CPT symmetry imposes that baryons and antibaryons have the same mass, in thermal equilibrium, their abundance would have to be equal. So a departure from thermal equilibrium is needed to generate an excess. And in addition, we need baryon number violating interactions, which also violate charge conjugation and CP symmetry since baryon number is odd under those quantities. So Steve devised a scenario that could give rise to the baryon number of the universe. In grand unified theories, there are heavy X bosons that mediate baryon non-conservation. That means when they decay into multiple channels with different values of the final state baryon number. And furthermore, because of CP violation, the branching ratios into baryon number violating channels can be different for the X particle and its antiparticle. Furthermore, if the decay occurs at a sufficiently low temperature, the inverse decay is blocked by a Boltzmann factor, which provides the needed departure from thermal equilibrium. And all that led to a formula for the ratio of baryon number to entropy in terms of those branching ratios and the amount of CP violation in those channels. Now, other people in 1979 were thinking about the origin of the baryon number of the universe in similar terms, but Steve's paper was characteristically general and culminated in a useful formula. None of those 1979 papers cited Sakharov's paper from 12 years earlier, which had clearly stated the criteria that needed to be satisfied for the generation of excess of matter over antimatter. Sakharov's paper was not known in the West at that time. Steve thought a lot about the cosmological constant and eventually came around to advocating an anthropic argument to explain its small but non-zero value. The idea of using the criterion that intelligent life is around to observe the universe as a means of making predictions about properties of the universe was already an old idea by then. Dickey, in particular, had argued that the age of the universe should be a few billion years, so that stars are old enough to have produced heavy elements, but also are still shining to support life. The cosmological constant problem is a severe, extreme example of a naturalness problem. From the point of view of a microscopic theory defined at the Planck scale, bare parameters need to be tuned to ridiculous accuracy to explain the observed very small value in Planck units of the cosmological constant. And in his 1989 review, Steve reviewed all of the then proposed solutions to this problem, found flaws in all of them, and concluded that the best explanation we have is the anthropic one. The argument went that if the cosmological constant is large and positive, then the rapid expansion of the universe would prevent gravitational condensation and therefore the formation of galaxies, stars, and life. If the cosmological constant is too large and negative, the universe would recollapse before life could appear. And the allowed values of the cosmological constant were not so different from the bounds that were known observationally at that time. Now, for that argument to make sense, we need a context in which we can envision fundamental constants being drawn from an ensemble of possible values that could be provided, for example, by the string landscape, by the vast number of solutions to the string theory equations of motion with different values of fundamental constants, together with an internal inflation scenario as a mechanism to populate that landscape. But it's never been particularly clear how to play this game, how to make sharp predictions based on the idea that the universe should allow intelligent life to observe it. At least that hasn't been clear to me. In 1998, when the evidence for a positive cosmological constant was found in measurements of redshifts of type 1a supernovae, some physicists were shocked. I was not. I don't think Steve was either. We had already discussed in the 1980s that there was growing evidence for a positive cosmological constant. For example, the inferred age of the universe at that time was shorter than the estimated age of stars and globular clusters, a problem that can be mitigated by a positive cosmological constant. And we agreed in the 1980s that if firm evidence is found for a positive non-zero value, the anthropic explanation is the best one that we have. And as far as I know, we don't have a better idea now. So how did Steve feel about that? Well, he said it would be a disappointment if this were the solution of the cosmological constant problems, because we would like to be able to calculate all the constants of nature from first principles. But it may be a disappointment that we'll have to live with. We've learned to live with similar disappointments in the past. And he pointed in particular to Kepler's disappointment that he couldn't explain the radii of the orbits of the planets in terms of geometrical principles like properties of Platonic solids. Later he said, in the multiverse, could you actually detect the presence of the other universes? I don't see how. Some feel it's not science. I don't agree with that. If there's some fundamental theory that implies the multiverse and we can experimentally test that theory in other ways, maybe in laboratory experiments, then because it implies the multiverse, we'll believe it. And he pointed out that, for example, we can't possibly observe distant galaxies similar to ours that are, say, 100 billion light years away, but we can reasonably infer that they exist based on our current understanding of cosmological theory. He made these remarks just a few months before he passed away. I have a couple of anecdotes that I like to think about when I remember Steve. One is the first time we met. It's 1974. I'm a senior in college. My then fiance, Roberta, now my wife, and I were in Boston for other reasons, and we thought it'd be fun to visit Harvard, where I was hoping to attend graduate school the following year, though I hadn't been admitted yet. So we're wandering the walls of, not the walls, we're wandering the halls of Lyman Lab, and we see Steve Weinberg's office door is open. He's in there alone, and we barge in. And I start explaining to him that I'm hoping to study at Harvard, and this is my fiance. And then I feel this surge of terrible embarrassment, and my face blushes bright red. I'm usually very shy. How could I have the audacity to barge into Steve Weinberg's office and introduce my fiance? And Steve looked at us expressionless for a few seconds. It seemed much longer, though. And then he smiled and he said, Louise and I did the same thing. So it turned out that they were engaged at the time that Louise and Steve scouted graduate schools together. So we had a friendly chat. I remember we discussed our shared admiration for Arthur Whiteman, who at that time was my senior thesis advisor and who Steve remembered fondly from his student days at Princeton. This one's from a few years later. It's 1981. I'm an assistant professor at Harvard now, and my parents are visiting from out of town. I think, boy, I bet they'd like to meet Steve and Louise. So we all had dinner in my backyard on a pleasant summer evening. I grilled chicken, and Steve said nice things about me because he knew my parents would like that. And somehow we started talking about how to make ice cream. And Steve said, you know, I've never understood why you put salt in an ice cream maker. And my dad, who was not a technical person at all, said, well, isn't it to lower the melting temperature of the of the ice so that the ice cream will be sure to solidify? And Steve slapped his forehead and he said, of course, I've never understood that before. And for the rest of his life, my dad would relish the time that he had given the great Steven Weinberg a science lesson. Steve was an optimist about the future of fundamental physics. A few years before he died, he said, the present generation of young physicists may envy those of us who had the excitement and delight of developing the standard model. This might be a mistake, just as it turned out that my generation would have been mistaken to envy the earlier heroes of quantum electrodynamics. Our newly minted experimentalists and theorists now have a chance to participate in making the next step beyond the standard model. They may even be able to see their way clear to the very high energy scale where a final theory will be revealed. Steve believed in the power of the human mind to understand the world. When I was a graduate student, I remember him telling me, some people say that we believe in our theories too fervently, that we trust them too much. But actually, the opposite is true. We don't trust our theories as much as we should. And the reason is that when you're sitting at your desk making squiggles on a piece of paper, it's just so hard to believe that those squiggles are really aligned with the way nature actually is. In the history of science, few squiggles have captured nature's hidden secrets better than those from the hand of Steven Weinberg. Thanks for listening.
For a couple questions? Everyone's in too much awe, I think, actually, at the moment.
I'm curious, I've heard that Steve eschewed toy models, whereas, a lot of hep-TH theorists tend to retreat to 2 dimensions, 3 dimensions, whatever. Is that true? Did he kind of explicitly eschew toy models in theory?
Well, one time he didn't. But generally speaking, I think Steve's belief was that models could be misleading because they always are wrong.
Sorry,
know-
the one time isn't a toy, it's the real world. I mean,
The one time isn't what?
if you're referring to the one time being the theory of leptons, it's not a toy.
Well, but you should read the paper. He thought it was. He didn't really think that could be the right model. And he says so explicitly. He says, of course, this speculative model isn't going to be really how the weak interactions behave, but it illustrates the principle that we can have a theory based on spontaneous breaking of gauge symmetry that explains how leptons are.
Well, I mean, I'm just saying that's very different from just explicitly, say, going to the wrong dimension, the wrong sign of the cosmological constant, et cetera. I'm just, yeah.
He thought he liked to be general. Models are, by their nature, specific and concrete. And he was more confident in conclusions you could draw from assumptions that would apply more broadly.
We have more questions? Okay.
I think I'm about to offend a number of people in this room.
Oh, I hope so.
And certainly my neighbor next to me, but it was my impression that Steve was not favorably disposed to string theory. And I know that I wasn't, but for the simple reason that it was hard to see how to test it. In fact, as far as I know, there are no known experimental tests that would tell us that string theory was right or wrong.
Is that a
That's
question?
my comment. No, I would like your comment, John.
Well, my
John,
comment is,
I have to say, I scarcely recognized you when I walked in the room. It's a
you
pleasure.
look
it's a-
exactly the same, Ken.
It's a pleasure to see you.
It is, yeah. We were we cohabitated at Harvard around 1980. Steve respected the successes of string theory, no question. And he, as far as the testability of the theory, I think he, regarded it as an open problem, which might have solutions to find convincing experimental confirmation.
Time.
Sometimes things take time, Ken. Well, yes.
Just a comment, since you mentioned Steve in writing his papers, I am one of those co-authors, and one of the papers you listed, it was a phys rev letter. And Steve wrote a wonderful introduction to the subject and the ideas in the paper, which I had to edit out because it wouldn't fit in the page limits of phys rev letters, which also meant editing out a number of the references that he wanted to include. And he didn't mind his words disappearing, but he really minded the references being taken out because there was no place to put those references in what we kept. As you said, he was very thorough about wanting to give all the preceding work that led to the paper.
Yeah, references were important to him, and he could be a little prickly when he didn't get referenced to, which I think was part of the reason he tried.
Many of the references that I edited out went to some of his previous work.
Well, you see why he was upset.
Well, let's thank John again for that beautiful talk.